The human eye and the colorful world. Prerequisites. To start this chapter requires a firm understanding of the following. Basic properties of light, like rectilinear propagation of light, reflection, refraction, image formation by spherical mirrors, image formation by spherical lenses. Know about some important terms in image formation. Learning objectives. Have the knowledge on the human eye. Understand the concept of power of accommodation. Gain the knowledge and skill on finding defects of vision and their correction. Understand the concept of refraction of light through a prism. Gain the knowledge on dispersion of white light by a glass prism. Recognize the part of light rays on atmospheric refraction and scattering of light. Introduction. What is refraction of light? How images are formed by lenses, and what are the nature, position, and relative size of those images? We can give the answers to above questions based on previous knowledge, which is studied in the chapter Light Reflection and Refraction. These ideas can help us to study of the human eye. The human eye. The human eye is the most valuable and sensitive sense organ, and it is a natural optical instrument. The eye is nearly spherical in shape with a slight bulge in the front part, and it enables us to see the beautiful, colorful world around us. Let us discuss about the important parts of the eye and their functions. Cornea. The front part of the eye is covered by transparent spherical membrane called cornea. Light enters the eye through cornea. Iris. Just behind the cornea is a dark-colored muscular diaphragm which has a small circular opening in the middle. Pupil. Pupil is a small circular opening of iris. The pupil appears black because no light is reflected from it. The dark center in the middle of the iris. The pupil determines how much light is let into the eye. It changes sizes to accommodate for the amount of light that is available. The iris regulates the light by adjusting the size of the pupil. Let us see how iris regulates and controls the amount of light entering the eye. When the intensity of light is more, or if it is a bright source of light, then the iris makes the pupil to contract, and as a result the amount of light entering the eye decreases. When the intensity of light is less, or if the light is dim, then the iris dilates the pupil so that more light can enter the eye. Eye lens. The eye lens is a concave lens made of a transparent jelly like proteinaceous material. The eye lens is hard at the middle and gradually becomes soft towards the outer edges. The eye lens is held in position by ciliary muscles. The ciliary muscles help in changing the curvature and focal length of the eye lens. Retina. The inner back surface of the eyeball is called retina. It is a semi-transparent membrane which is light sensitive and is equivalent to the screen of a camera. The light sensitive receptors of the retina are called rods and cones. When light falls on these receptors, they send electrical signals to the brain through the optic nerve. The space between the retina and eye lens is filled with another fluid called vitreous humor. blind spot. It is a spot at which the optic nerve enters the eye and is insensitive to light, and hence the name. Let us discuss about accommodation of the eye and power of accommodation. Accommodation of the eye, the process by which the ciliary muscles change the focal length of an eye lens to focus distant or near objects clearly on the retina, is called the accommodation of the eye. Power of accommodation, the ability of the eye to focus objects lying at different distances, is called the power of accommodation of the eye. How does an eye focus objects at varying distances? When the ciliary muscles are relaxed, the eye lens becomes thin. Thus, its focal length increases and we see the distant objects clearly. When the ciliary muscles are contract, then the curvature of the eye lens increases and the eye lens becomes thick. Thus, its focal length decreases and we see the nearby objects. In brief, it is adjustment of the focal length of the eye lens which enables us to focus on objects situated at different distances. Least distance of distinct vision, near point. Near point or least distance of distinct vision is the point nearest to the eye at which an object is visible distinctly. For a normal eye, the least distance of distinct vision is about 25 centimeters. However, it varies with age of the person. For example, for infants, it is only 5 to 8 centimeter. The far point of the eye. Far point of the eye is the maximum distance up to which the normal eye can see things clearly. It is infinity for a normal eye. Cataract. The crystalline lens of people at old age becomes milky and cloudy. This condition is called cataract. This causes partial or complete loss of vision. It is possible to restore vision through a cataract surgery. Range of vision. The distance between the near point and the far point is called the range of vision. Defects of vision and their correction. The eye may gradually lose its power of accommodation. In such conditions, the person cannot see the objects distinctly and comfortably. The vision becomes blurred due to the refractive defects of the eye. There are mainly 3 common refractive defects of vision. These are 1. Myopia or nearsightedness, 2. Hypermetropia or farsightedness, and 3. Presbyopia. These defects can be corrected by the use of suitable spherical lenses. We discuss below these defects and their correction. Myopia. The light from a distant object arriving at the eye lens may get converged at a point in front of the retina in the vitreous body. This type of defect is called nearsightedness or myopia. Let us observe these cases and then you can understand the concept myopia. In the case of normal eye, the light rays from the object fall on the eye and converge on the retina. In the case of myopic eye, the light rays from the object fall on the eye and focuses the light at a point in front of the retina in the vitreous body. The correction for myopia. To compensate this, we interpose a concave lens between the eye and the object with the diverging effect desired to get the image focused on the retina. Hypermetropia. If the eye lens focuses the incoming light at a point behind the retina, this defect is called farsightedness or hypermetropia. Let us observe these cases, and then you can understand the concept. Hypermetropia. In the case of normal eye, the light rays from the object fall on the eye and converge on the retina. In the case of hypermetropic eye, the light rays from the object fall on the eye and focuses the incoming light at a point behind the retina. The correction for hypermetropic eye. A convergent lens is needed to compensate for the defect in vision. Presbyopia. What is presbyopia? Presbyopia is a common type of vision disorder that occurs at your age. It is often referred to as the aging eye condition. Presbyopia results in the inability to focus up close, a problem associated with the refraction in the eye. How does presbyopia occur? Presbyopia happens naturally in people as they age. The eye is not able to focus light directly onto the retina due to the hardening of natural lens. Aging also affects muscle fibers around the lens, making it harder for the eye to focus on up-close objects. The ineffective lens causes light to focus behind the retina, causing poor vision for objects that are up close. When you are younger, the lens of the eye is soft and flexible, allowing the tiny muscles inside the eye to easily reshape the lens to focus on close and distant objects. Refraction of light through a prism. In the previous chapter, you have learned how light gets refracted through a rectangular glass slab. For parallel refracting surfaces, as in a glass slab, the emergent ray is parallel to the incident ray. However, it is slightly displaced laterally. How would light get refracted through a transparent prism? Consider a triangular glass prism. It has two triangular bases and three rectangular lateral surfaces. These surfaces are inclined to each other. The angle between its two lateral faces is called the angle of the prism. Fix a steel of white paper on a drawing board using drawing pins. Place the glass prism on it in such a way that it rests on its triangular base. Trace the outline of the prism using a pencil. Draw a straight line PA inclined to one of the refracting surfaces, say AB of the prism. Fix two pins, say at points P and Q on the line PA as shown in figure. Look for the images of the pins fixed at P and Q through the other face AC. Fix two more pins at points R and S such that the pins at R and S and the images of the pins at P and Q lie on the same straight line. Remove the pins and the glass prism. The line PE meets the boundary of the prism at point E. Similarly, join and produce the points R and S. Let these lines meet the boundary of the prism at E and F, respectively. Join E and F. Draw perpendiculars to the refracting surfaces AB and AC of the prism at points E and F, respectively. Mark the angle of incidence, angle I, the angle of refraction, angle R, and the angle of emergence, angle E, as shown in figure. Here, PE is the incident ray, EF is a refracted ray, and FS is the emergent ray. You may note that a ray of light is entering from air to glass at the first surface AB. The light ray on refraction has bent towards the normal. At the second surface AC, the light ray has entered from glass to air. Hence, it has bent away from normal. Compare the angle of incidence and the angle of refraction at each refracting surface of the prism. Dispersion of white light by a glass prism. You must have seen and appreciated the spectacular colors in a rainbow. How could the white light of the sun give us various colors of the rainbow? Before we take up this question, we shall first go back to the refraction of light through a prism. The inclined refraction surfaces of a glass prism show exciting phenomenon. Let us find it out through an activity. If a prism is placed in a room and a narrow beam of white light is allowed to fall on one of its refracting faces, what do you observe? It is found that light coming out from the other face of the prism is split to 7 colors. What are the 7 colors that you see on the screen? The various colors seen are violet, indigo, blue, green, yellow, orange and red. This phenomenon, the splitting of light into its component colors, is called dispersion of light. The band of the colored components of a light beam is called its spectrum. Why does this happen? The acronym VIBGY will help us to remember the sequence of colors. We have seen that white light is dispersed into its 7 color components by prism. Why do we get these colors? Different colors of light bend through different angles with respect to the incident ray as they pass through a prism. The red light bends the least, while the violet the most. Thus, the rays of each color emerge along different paths and thus become distinct. It is the band of distinct colors that we see in a spectrum. Isaac Newton was the first to use a glass prism to obtain the spectrum of sunlight. He tried to split the colors of the spectrum of white light further by using another similar prism. However, he could not get any more colors. He then placed the second identical prism in an inverted position with respect to the first prism. This allowed all the colors of the spectrum to pass through the second prism. He found a beam of white light merging from the other side of the second prism. This observation gave Newton the idea that the sunlight is made up of 7 colors. Any light that gives a spectrum similar to that of sunlight is often referred to as white light. A rainbow is a natural spectrum appearing in the sky after a rain shower. It is caused by dispersion of sunlight by tiny water droplets present in the atmosphere. A rainbow is always formed in a direction opposite to that of the sun. The water droplets act like small prisms. Atmospheric refraction. We've observed some natural phenomena in our daily life, such as the apparent random wavering or flickering of objects seen through a turbulent stream of hot air rising above a fire or a radiator. The twinkling of stars is a similar phenomenon. This wavering is thus an effect of atmospheric refraction, refraction of light by the Earth's atmosphere in our local environment. Twinkling of stars. The twinkling of a star is due to atmospheric refraction of starlight. The scientific name for the twinkling of stars is stellar scintillation or astronomical scintillation. Stars twinkle when we see them from the Earth's surface because we are viewing them through thick layers of turbulent, moving air in the Earth's atmosphere. Stars, except for the sun, appear as tiny dots in the sky. As their light travels through the many layers of the Earth's atmosphere, the light of the star is bent, refracted, many times and in random directions. Light is bent when it hits a change in density, like a pocket of cold air or hot air. This random refraction results in the star winking out. It looks as though the star moves a bit, and our eye interprets this as twinkling. Stars closer to the horizon appear to twinkle more than stars that are overhead. This is because the light of stars near the horizon has to travel through more air than the light of stars overhead, and so is subject to more refraction. Also, planets do not usually twinkle because they are so close to us. They appear big enough that the twinkling is not noticeable, except when the air is extremely turbulent. Stars would not appear to twinkle if we viewed them from outer space or from a planet or moon that didn't have an atmosphere. Apparent position of Sun. Because of atmospheric refraction, we do not see the Sun or the stars in its true position except when it is directly overhead. As a ray of light from the Sun enters Earth's atmospheric at B, it continuously bends towards the radius of the Earth. The ray of light will reach the observer at O, as if it had come in the direction AO instead of in its true direction BO. Consequently, we do not see the true position of the Sun. It is due to atmospheric refraction that the Sun is visible before actual sunrise and after actual sunset. The Sun appears to rise 2 minutes before the actual rise, and it continues to be seen 2 minutes after it has actually set. Therefore, the day becomes longer by 4 minutes due to atmospheric refraction. Scattering of light. We've across some wonderful phenomena in our daily life, such as the blue color of the sky, color of water in deep sea, the reddening of the sun at sunrise and the sunset. Or, what is the reason behind these natural phenomena? For this, first we shall discuss about scattering of light. Scattering of light. When a beam of light falls on an atom, it causes the electron in the atom to vibrate. The vibrating electrons, in turn, re-emit light in all directions. This process is called scattering. Earth's atmosphere contains air molecules and other tiny particles. When light from the sun passes through the atmosphere, it gets scattered by the large number of particles in the atmosphere. According to Rayleigh law, the intensity of scattered light varies inversely as the fourth power of the wavelength of height, 1 by h power 4. Tyndall effect. John Tyndall was the first one to explain about the color of the sky in the year 1859. He stated that the color blue scattered more than that of red due to the shorter wavelength in a case where the light has to pass through a clear fluid that contains suspended small particles. Our planet Earth consists of various mixtures of particles like smoke, molecules of air, dust particles and water droplets. These diffused particles reflect the light before it reaches the Earth. The scattering of light by the colloidal particles is known as the Tyndall effect. The size of the particles determines the color of the scattered light. This statement can be proved with the help of a simple experiment. Allow a beam of light to pass through a tank of water with a slight mixture of soap or milk in it. If you wash the beam from a side, you can notice that the beam scatters blue light, but when you thoroughly observe the beam from the end, then you will find that the beam is reddened after it has passed through the tank. Why is the color of the clear sky blue? Since the wavelength of blue color is smaller than the wavelength of red color, lambda b less than lambda r, scattering of blue light by particles in Earth's atmosphere is very large. For this reason, we see a blue sky. Although violet light is scattered more than blue light, our eyes are not very sensitive to violet light. Color of the sun at sunrise and sunset. At the time of sunset or sunrise, the sun is near the horizon as shown in the diagram. The rays from the sun must travel more kilometers through the atmosphere than at noon. Therefore, more blue is scattered from the sunlight. The removal of blue leaves the transmitted light more reddish in appearance. Therefore, sun looks reddish at the sunset or sunrise. Summary. The human eye is the most valuable and sensitive sense organ, and it is a natural optical instrument. The important parts of the eye: cornea, iris, pupil, eyelid, retina. Power of accommodation. The ability of the eye to focus objects lying at different distances is called the power of accommodation of the eye. Least distance of distinct vision. Near point. Near point or least distance of distinct vision is the point nearest to the eye at which an object is visible distinctly. The far point of the eye. Far point of the eye is the maximum distance up to which the normal eye can see things clearly. It is infinity for a normal eye. The twinkling of a star is due to atmospheric refraction of starlight. Scattering of light. When a beam of light falls on an atom, it causes the electron in the atom to vibrate. The vibrating electrons, in turn, re-emit light in all directions. This process is called scattering.